Okay, so welcome everybody. It's a pleasure to have Bjørn Kjos-Hanssen with us today from University of Hawaii, and he will tell us about a one-parameter family of metrics connecting Jaccard distance to normalized information distance. Bjørn.
Thanks, Damir. Yeah, thanks everyone for coming, and thanks for inviting me to this seminar. So this is about a paper that was started around May or April. It was sort of inspired by this coronavirus and the genome sequence of the virus and things like this. So the computability part is the normalized information distance, which is a distance function defined in terms of Kolmogorov complexity. Jaccard distance is a sort of simpler concept that arises all throughout science. See, this is some joint work with some students, some support by an insurance company. Let's see. Yeah, so there is all kinds of distance functions you can define on, let's say, finite sets. And the main point of this paper is that the normalized information distance that involves Kolmogorov complexity and this Jaccard distance, which is very much used, they are actually the endpoints of a family of metrics in a certain sense. So that's what we're going to see what that means. Yeah, so in all kinds of areas of science, these metrics are very popular for saying how closely do things seem to be related if you don't really know, but you want to just measure it based on the data. Let's see. So for example, there was this paper here in a journal called Bioinformatics, where they introduced one possible way to measure distance between these biology genome sequences. Then there is a maybe more familiar paper by Chen, Li, Ma, and Vitani called the similarity metric, where they say, okay, let's measure distance between finite strings in terms of this function here. So it's the maximum of the conditional Kolmogorov complexity of x given y and the other way around. And then they try to kind of normalize it to have maximum 1 by dividing by the maximum of the two Kolmogorov complexities. And it's the prefix-free Kolmogorov complexity, although I don't think it matters. So they prove that this is a kind of a metric, and they referred back to this paper by Lee and Badger, and they said we don't like that their way of doing it, because their way was more using addition instead of maximum. Now later in 2017, Raf and Nicholas, they were looking at some totally different topic, malware detection, and they said, sort of, let's take the normalized information distance, but go back to the form that was in the bioinformatics paper. So there seems to be some going back and forth. And so that was, in a way, the inspiration. So you have people going back and forth between these two possible ways of making a distance function. So yeah, it turns out they're like the extreme points of a family of metrics. Okay, so what is it really we're talking about? Let's see. So the Jaccard distance. So I have two sets, two finite sets x and y. It's just defined like this. So it's the kind of thing that's so simple that even if you hadn't heard of it, you might just come up with it yourself. So it's just saying, if I want to compare how far apart two sets are, just think in terms of the Venn diagram, right? Like how many points are in one but not the other compared to how many points are there overall. And the fact that this actually gives you a metric that satisfies the triangle inequality is something that's been reproven over and over by lots of authors. And it doesn't seem to have a really obvious proof. Like, it seems it's a very simple statement, but if you try to prove it, I think you tend to end up with lots of sort of little calculations and just verify it. Okay, and the analog of this is that's similar to normalized information distance is as follows. We just say, instead of adding up these two left and right moon-shaped regions of the Venn diagram, we just take the maximum of them and also maximum in the denominator. So far we then have the setting of Kolmogorov complexity, and we have the setting of cardinality of a finite set. There is another way that this analogy extends to, which is entropy. So in this paper, hierarchical clustering using mutual information, they study this metric here, which is called the Rieske distance. And so this, as you can see, is similar to the, not the NID, but the other, so similar to the Jaccard distance. So we're just saying we take the entropy of random variable x given y plus the entropy of x, oh, it should of course be y given x, divided by the joint entropy. And this is 1 minus the mutual information divided by the joint entropy. And so it turns out that in this paper that I'm presenting, the proofs end up also working for entropy. So that's good. We get a similar family of metrics involving entropy. Okay, so yeah, there's a lot of papers about this topic. So one sort of general setting that you can start from is this thing called Tversky metrics, or Tversky ratio models. Let's see. So first we have just the idea of a semi-metric, which is a metric but you don't require the triangle inequality. And so that could be useful for some kind of similarity notions. Okay, and so the general setting where this family of metrics is going to fit in is, well, one general family, one general setting is this Tversky index. So now we say, well, the distance is going to be 1 minus this, but so the similarity is how much do they have in common, and then we just make the denominator depend on some parameters to give us some flexibility about how to measure these similarities. And you may notice there's a denominator. It could be 0, but in order to get a metric, of course, we just define the distance is 0 for, if both sets are empty. And then here's just a little technical lemma that says that that's fine. We can treat the case of the empty set separately and nothing bad will happen. Okay, so how about some examples of these? So this general setting, it has Jaccard distance as one example. There are some other exotic things like the Simkiewicz-Simpson coefficient, which is defined this way. It's not a metric. So even if you take 1 minus it, so even if you try to make it look like a metric, it doesn't quite work. And another one that's, I guess, famous in some quarters is the Sørensen-Dice coefficient. This is another variation of this. Okay, so we can make a general thing. So we can say, well, maybe we are interested in the minimum and the maximum of these two sides of the Venn diagram. Yeah, and then we can make a general formula like this. We might even have a bias, but I'm not interested in that. I'm going to say that's always 0. And then we have alpha that's used to weigh how much do we care about the minimum and how much do we care about the maximum. So maybe we only care about the maximum. That would be like the NID, normalized information distance. Or if we care about them equally much, then it ends up just being adding up the two sides. So alpha is between 0 and 1. Okay, so then if we take 1 minus this, we get a little bit complicated looking function like this. So this is the distance between x and y. And depends on these two parameters. Okay, so here's the theorem. So is this a metric? That was the question. And so alpha has to be between 0 and 0.5. And that means that we cannot put more weight on the minimum of the two cardinalities. We should put at least as much on the maximum. And this other parameter beta, that's not as interesting. That has that sort of upward closed what that can be. So, but that should be at least 1 over 1 minus alpha. Okay, so here's the picture that fits the title of the talk, the one parameter family of metrics. So the green, or very light green, indicates all the parameter values for alpha and beta that do give us a metric. And the pink, or very light reds, indicates we don't get a metric. So we have the Simkiewicz in the red, the Dice coefficient is in the red, and then Jaccard and the NID are the two extreme points of the green region. So I'm writing NID, but it's really the analog when you translate Kolmogorov complexity over to cardinality. Okay, now the proof is sort of elementary. Let's say we'll use, for example, little lemmas like this. And little lemma like this. Okay, so then one part of the theorem says that the set of betas for which this is a metric is upward closed. Okay, now to get into a little more detail, let's see. Sometimes it's a question, what's the most convenient notation when you're working on some topic? This alpha bar is 1 minus alpha. That's a pretty common one. If you do a lot with these cardinalities of intersections, you may want to just use notation like this. And then here's one I found really convenient. So just the cardinality of the set difference of x and y, let's just call it x sub y. Okay. So one starting point is, if we don't even look at the denominator, but just the numerator, call that delta. So that was this parameter alpha times the smallest of the two parts, little m, plus alpha bar times the bigger part. And then we would just want to see, does that satisfy the triangle inequality? And you can show that that happens just if alpha less or equal to half. So in other words, we put more weight on the bigger side of the Venn diagram. So it has a little bit of a funny story. So initially, I didn't have any intuition for this, but just using some coding, it was sort of clear what the answer was going to be. And also, I verified this proof in Lean, the proof assistant. And that may seem like an unnecessary waste of time, but in the sense that this wasn't a very complicated, questionable theorem. But at least for me, it turned out that doing that was a way to improve the proof and see what's really going on. And in fact, there's this little identity here that's elementary, but I guess I hadn't really thought about this before. So this is saying that if you look at the number of elements that either belong to X and not Y, or they belong to Y and not Z, or they belong to Z and not X, that's the same as the elements that belong to X and not Z, or Z and not Y, or Y and not X. Oh, and this is plus because these are all disjoint. So that one turned out, after analyzing the proof with using lean, it turned out that this is sort of the nicest way to say, to express the proof, and this is the main ingredient. Okay, so then we get this this theorem again. Yeah, so that's that. Now, this is the computability and application seminar. So one thing you can say about computability here is, what if we go back to Kolmogorov complexity? So we take the analogy back in that direction. So then we have sort of the mutual information of two strings. I'm not sure if I'm allowed to call it that, but that ends up being then the sum of the Kolmogorov complexity minus the complexity of the pair. And then we define analogously this function. And now we know that Kolmogorov complexity is upper semi-computable, because as you find more and more descriptions, you can approximate the complexity from above. So any expression involving this k of x, you might hope it should be lower or upper semi-computable. On the other hand, if k appears in several places, you wouldn't really expect it to happen. So there was a paper by Theorem. Sorry, now I got it. Let me get back. So there was a paper by Theorem, Torenfleet, who I also see in the audience today. Thanks for coming. And Vitani. And they showed that this is not an upper or lower approximable function in the case that they looked at, which is the normalized information distance. So alpha is 0 and beta is 1. So I looked at the proof. It's sort of interesting how in one part of the proof, what they say is that we can look in particular at the case when x is equal to y. So if this were approximable, then it would also be so when x is equal to y. And then, well, the complexity of x given x is just maybe a constant, like just equal to 1. Now this doesn't translate exactly over in the other setting, because in the Venn diagram, or the entropy, entropy of x given x is just 0. There's no constant. So it's a question whether you could find any such alpha and beta. You see, I was trying to do some elementary reasoning about it, and maybe concluded that if it's going to work, alpha, let's see, I guess what I couldn't really rule out was that alpha is like Chaitin's omega, like it's lower semi-computable. Okay, so that's a bit of an esoteric question. Okay, yeah, so what about entropy? So there is a connection between these Venn diagrams and entropy, and that helps the same proof, the same ideas transfer over. This was studied by McGill and Hu Kuo Ting a long time ago. It turns out that it involves some sign measures. So that means that some of these mutual informations can be negative, as I'll show in a little bit. The basic observation is this, that if you have this the Venn diagram generated by 3 sets, and you have the 7 minimal regions, the ones that cannot be broken up as unions, then their cardinalities can be defined from just sort of the positive information of the cardinalities of the various unions. So that's a pretty basic thing, but maybe it's not something one would have thought about or considered. Yes. For example, the difference can be expressed this way, intersection as well, and the intersection of 3 things can be expressed this way. Now, this does involve some pluses and minuses, so it's not immediately obvious maybe that all of these things are positive. If they're cardinalities, yes, they're non-negative. If they're entropies, that's something to look into. Yeah, so now we can define things like this: the mutual information of 3 random variables x, y, and z. We can also define the mutual information of 2 of them given 1. And this is going to be the part of the Venn diagram that's in the intersection of x and y, but outside of z. Okay. And it turns out the only thing that can be negative is actually the middle of the Venn diagram, the mutual information of x, y, and z. Now, in the proof that I suggested above involving cardinality, that involves some manipulation or facts about cardinality. But if you look carefully at the proof, it never uses the fact that the cardinality of this middle of the Venn diagram is non-negative. And so that's good. So that gives some hope that we can just use the same proof for entropy. And that's what I'm claiming works. Yeah, so the definition of this mutual information of 3 random variables is like this. So, what is the information they have in common, x, y, and z? It's the information x and y have in common, but then you have to subtract what's in common after z. The information in z is known. Okay. Now here, the special notation here is that semicolon means you are looking at the mutual information, whereas the comma means you have the joint entropy. So it's a little bit like intersection and union, or semicolon and comma. Right, so for example, if we write mutual information x semicolon y comma z, it's the mutual information between the random variable x and the vector or pair of random variables y and z. So, so what's going on with this entropy is like this. So suppose you just have a finite set. Right? We're not talking about infinite sets here. The random variables are real valued, but it's all on the finite set, which is basically the bits or the possible outcomes. So if we then consider r to the omega to be all the real valued functions, we want real valued random variables on this set. Okay, and then so that's just a set theoretic thing. But on the other hand, we can also look at all the probability distributions on this finite set omega. And now this can interact. For example, we can say for each probability distribution now, all these functions are now random variables, and they are jointly distributed. Like if I pick a point in capital omega, I get a value for all these random variables. So it's yeah, you could call it a space, since you could in principle do arithmetic operations on these random variables, but that's not the point. Okay, so here's a statement of the theorem that's analogous for entropy to the theorems for cardinality and for Kolmogorov complexity. So all the same stuff, just yeah, now being exactly the same means that the joint entropy is 0. Actually, that might be, let's see, maybe that's a typo, but now that I think about it. It should be the entropy of x given y plus the entropy of y given x is 0. Okay. All right, and so the theorem that I alluded to regarding entropy is just this, that if you have random variables, then most of these quantities you can look at are non-negative. Like the entropy is non-negative, and the entropy of a pair or union, and also these conditional mutual information, but not the triply mutual information. So this is the basic thing that's in the information theory textbooks, for example, and involves Jensen's inequality. Yeah, now because I didn't put the definition of entropy, but it's like the expected number of bits of information that you receive when you find out the value of a random variable. So it's like the expectation of negative log 2 of the probability of the outcome that did happen. Okay, so here's an example, and I think this will also translate into Kolmogorov complexity. So 3 strings with negative mutual information. I don't know if anybody wants to suggest why these 3 might have, or what's going on with these 3 strings here. It's just that, so each one is the sum of the other 2 mod 2. And so if you work through this definition, it means they have negative mutual information, because any 2 of them are independent, but if you're given the third one, that determines whether the first 2 are equal or not equal. So one possible response is that this isn't really mutual information, because that intuitively should not be allowed to be negative. And so you can make other definitions for that phrase. So you can say, let's use what Watanabe called total correlation. So just the sum of entropies minus the joint entropy. And then it ends up being positive. And I think in computability, for example, in this recent paper by Romashenko and Zeman, they said, there's no mutual information for more than 2 strings. Okay, so here's something interesting. So computability theory related, that this a random variable in a way just corresponds to a partition of this set omega, because we have finitely many outcomes, and then we need to say, maybe if every outcome gives us a different value of our random variable, then we have the greatest possible entropy on that probability space. But maybe there are several outcomes that give the same value that reduces the entropy. So that means actually each random variable just corresponds to a partition of the set. So you can actually think about this even in terms of Turing degrees. You know, sometimes in computability we want to embed something into the Turing degrees, like a semi-lattice, or maybe you want to embed a semi-lattice as an initial segment of the Turing degree. So the degrees of solvability, you know, under Turing equivalence. And in doing that, in fact, the typical technique is to use, so we have a semi-lattice or lattice, and then we want to represent it as a lattice of equivalence relations. And that's maybe not obvious initially. You know, why would you want to do that? Why not just work with the lattice as it is? Well, so equivalence relations are ordered by finer and coarser equivalence relations. And it turns out that you can take a lattice and you can find a set of equivalence relations that has the same order structure. So now, so the way that this works in the Turing degrees is that the different places in a lattice correspond to different equivalence relations, and at the top, so the highest Turing degree, we have the equals relation, just the identity, and then at the bottom we have the everyone equivalent relation. And so if you think about that, it's saying that the equivalence relations with high entropy, they are the ones that end up being high up in the Turing degrees. Now, the entropy is always just a number. So if you just order by entropy, it's going to be a linear order. On the other hand, you could look at the entropy as a function of this underlying probability space of the probabilities of the various outcomes, P1, P2, P3. And then I conjecture then that such a function, you know, the ordering of such functions, the entropy of various random variables as a function of the probability or the probabilities involved, this will be the same as the ordering of the lattice. So we look a little more in detail at this. You know, when we make an initial segment of the Turing degree, so something like a minimal Turing degree or some other lattice that's embedded into the Turing degrees with nothing below any element except what's in the lattice. So the way this is done is you make a function g, and then for each partition in this representation by equivalence relation, you have a function gk. And it's just obtained by just mapping to the lower partition. So if you want to be concrete, you could say it's using the lattice table where certain numbers get mapped to other numbers, but where you identify more numbers as you go to a coarser equivalence relation. So actually, if you look at it that way, then the different functions that are used in the construction are called G, I, G, J. They should have the entropy corresponding to the Turing reducibility. And in a way, we can see something like that is happening because the Kolmogorov complexity will be just bounded or ordered the same way as the lattice, maybe up to a constant, because all you're doing is that you're applying some map, like maybe 0 and 2 get identified and 1 stays alone. And the use is identity bounded for this map that sends GJ to GI.
Can I ask a question? Why are you switching from K to C from the prefix Kolmogorov complexity to the non-prefix Kolmogorov complexity?
No real reason.
Okay, thanks.
Yeah. So yeah, one way of thinking about this is that how should the Turing degrees be ordered? Is it really appropriate to say that the computable sets are at the bottom? In a way, being computable is the best thing. So they should put the computable Turing degree on top. Well, there could be all kinds of things said about that, and it doesn't really matter in the end. But one thing you could say is that this way, the larger Turing degrees are the ones corresponding to higher entropy. So we got it right with the ordering of the Turing degrees. Now, when we do get these representations of lattices by equivalence relations, that's using some work that's been done already by lattice theorists. And they are not coming at it from the point of view of entropy. They a long time earlier said, okay, we're interested in maybe the lattice of all subalgebras of an algebra, or we're interested in quotient algebras. This would be of interest all over mathematics. So therefore, we are looking at these different partitions forming quotient structures. And in that setting, so it's not really the case that you get the more complicated things in one direction and simpler things in the other direction. This is obvious that any structure is a quotient of a free structure. So a free structure is maybe very simple in some sense, and you take a quotient, you get something more complicated. And then you take a quotient again, and now maybe you have just one element. So if you look at it that way, the most complicated things are somewhere in the middle. So this use of these equivalence relations in computability theory, right? Maybe it's a little bit of a lucky stroke that representing lattices by equivalence relations was of interest for other reasons in other areas of math, but in computability, it's like, the identity relation leaves a lot of ways open, a lot of things open, a lot of possibilities open, and so we can say that the entropy is higher. Okay, so here are some of these the papers from various areas that I have been referring to. I was also considering to present using a whiteboard and do some more examples, but I think I can stop here for now, and then if